Actually, I forgot to share the link. I hope any issue
In Model Simulator, for latest version also facing the same issue.
in latest version also, no? Okay. Have you tried remaining first version, 17th version?
No, I'll try.
Okay, today try with the 17th version also. If it not getting, then we will install Questasim.
Sorry to interrupt. So far, I did not install the concern software.
Yeah.
Actually, I don't know the details.
Okay, no problem. I will share you the recorded session till now, whatever completed. Till now, just a basics are completed. Okay. Just demo sessions on digital logic design. Just from yesterday only, Verilog session started. Verilog not yet started yesterday. Just how to install the tools I have explained. And in digital electronics, still combinational circuits only completed. Okay. I think you already know the digital electronics. If you revise once, you will get understand what are the circuits. Okay, from now onwards, digital electronics we are discussing in the weekends. Weekend digital electronics, weekdays Verilog HDL. Okay.
Okay, okay.
So I will tell you how to install the tools. Actually, for Verilog HDL, you already know maybe what is mean by Verilog HDL. Verilog means it's a hardware description language. Okay, so hardware description language is used to describe the digital circuits, digital hardware circuits, or analog hardware circuits. Okay, for analog circuits we have analog hardware description language. One is a Verilog HDL is there. In digital we have a digital Verilog HDL. Okay, we have a VHDL also, but comparatively we are not using VHDL because it is a complex programming, and also we need to use standard libraries, so it is not a efficient use, like we cannot use easily. Okay, learning wise or implementation wise, complexity is more. That's why Verilog HDL is mostly preferred. Okay, so to write the program using Verilog HDL, we need a tools. So one is a synthesis tool, another one is a simulation tool. Synthesis in the sense generating the circuit netlist. Okay, so if you see the flow, is the PPT visible, everyone?
Yes.
I'm moving slides.
Yes, ma'am.
Is the PPT visible? Okay. How many of you joined for the first demo session now? Did you all join for the first demo session? Okay. If not, no problem. Again, we will discuss. Okay. So coming to the VLSI design flow. In VLSI design flow, we have a front-end design and front-end domain and a back-end domain. Okay. So you are all joined for the front-end domain design verification and also physical design, right? So we will discuss today what is mean by front-end domain, what are the different steps, and what is mean by back-end domain, and what is mean by DFT insertion, logic synthesis, and then we will start with the Verilog HDL. Okay, so first VLSI design flow. Before whoever facing some errors, I think Pranita is facing error to install the tool, right? So by end of the session, you can share your screen and we can discuss. Okay, remaining anyone facing the issue? What about remaining? Are you facing any problem? Have you tried to install? What about Sumo already installed? Sagar, Ritesh, Madhumita, and Sri Vishnu.
Yeah, ma'am, I have Vivado.
Okay. Remaining?
I also have Zain's, ma'am.
Okay. Okay, so fine. No problem. Any tool is fine. in Vivado and Xilinx, we can do both synthesis and simulation. Okay, I think only Pranita is going to face error issue. Okay, no problem. We will discuss. Okay, see here. VLSI design. In VLSI design, we have a front-end domain, back-end domain. Okay, in the front-end domain, first of all, to design a processor, to manufacture a processor, we need to follow some steps. Okay, we have a different types of processors, right? Like ASIC design, FPGA design, system on chip design. What is the difference between ASIC, FPGA, and system on chip? Can anyone tell? What is the difference between ASIC, FPGA, and system on chip?
ASIC is application specific, ma'am. FPGA is, I mean, sir, once we have done for one specific application, we can't reprogram. And FPGA is for reprogrammable. We can erase the memory or we can reuse for the other applications. SOC, system on chip, like I don't know that much, ma'am.
Okay, fine. What about remaining? Ritesh? Shanita? Madhumita? Okay, ASIC chips are application specific integrated circuit, which are a permanent processor. That means once we dump a data into the chip, it is a permanent. We cannot reprogram it again and again. Okay, so applications like any processor, whatever the processors we are using in the laptops, mobile phones, or any digital gadgets, those all are permanent chips. If any chip damage, we cannot reprogram it, or we cannot do any modifications like that. Okay, we just need to throw. So that is not useful once it is repaired. But FPGA is not like that. FPGA is like a temporary chip. It's a board. Like in IoT applications, we use Arduino boards. In embedded systems, we use Raspberry Pi boards. Like where we dump the program into some board, into some chip, and we can use for a specific application. Okay, suppose in your BTech level or MTech level, you are working on some projects, right? VLSI projects, you want to design a traffic light controller or some digital alarm or digital clock. There are a lot of projects, processor related projects are there. So mostly if you want to implement those designs into the hardware, we mostly prefer the FPGAs. FPGA is also hardware like ASIC chip, but ASIC chip is a permanent chip which is designed for mostly from product based companies for devices. Okay, whatever the devices we are using. But FPGA is a board which is used for just like a projects. And in the most of the industries also, if they want to dump some permanent program into the ASIC chip, they never dump directly into the ASIC chip without cross check. Okay, they will cross check by using the FPGA chip first. They have a complex FPGAs, not like a student version. Whatever we use a small FPGAs, it's not like that. They have a complex versions of FPGA. In that, they will dump the program and check according to the specification whether it is working properly or not. Okay, so that's why FPGA is a reprogrammable. You can dump one time, you can do with some functionality, again you can reprogram it, you can use for some other project again, like that. Okay, but coming to the system on chip, ASIC chips are older versions. Okay, like in 2000 time or 2010, that time we use the ASIC chips. It's a processor in a motherboard. Suppose I will show you the difference between ASIC chip and SoC. Suppose there is a motherboard. If you see, there are some computers which are bulk in size. CPU will be there, central processing unit. In the central processing unit, there will be a motherboard. If you observe in olden days, on top of motherboard is nothing but PCB board. That one is a PCB board. On the PCB board, we insert some processor. There will be some memory slots, PCIe slots will be there, North Bridge IO, South Bridge IO, and there will be different ports, USB ports or some DVD player ports will be there. So the size of the board is a very bulk size, and that too, that is a PCB board. Okay, but coming to the system on chip is not like a PCB board. Okay, we will integrate every circuit, every component into a single chip. There will be a chip, small chip. Into the chip, we will put a processor, we will put memory modules, North Bridge IO, South Bridge IO, graphic processors will be put in the same chip. Okay, if you see olden computers, if you want to use some graphics related, some video gaming, or if you are editing something related to the images and all, we will buy separate graphic processor and we will integrate that graphic processor in the motherboard. Separate slot will be there for graphic processor. We need to buy separately as per your requirement. For normal usage, no one will buy graphic processor. Mostly whoever using for video editing purpose or cameraman, mostly those will use the graphic processor. They will buy separately and they will integrate according to their usage. Okay, but nowadays in SoC, we are using monolithic chips and multi-chiplets. Everything is a multi-chiplet based. Multi-chiplet means everything, the graphic processor, the normal processor, digital signal processor, everything integrated on a single chip itself. Okay, that's why we call it as a system on chip. Okay, I will show you the difference. So these are all like motherboards. In these motherboards, we use ASIC processors, ASIC chips. Okay, all components are connected separately. If any component is failure, like any component damaged, we can buy new component and we can fit easily. Okay, but system on chip is like a everything inbuilt on a small chip like this. Here is a processor, the system on chip, and see here how the all components are integrated on a single chip here right side. Okay, so these all are different versions of SoCs because every company have their own SoCs. Intel have their own processor, their own SoCs. Nvidia have their own graphic processor and SoCs. Okay, so that is what the main difference between ASIC chip and SoC chip. ASIC chips are older version, SoC chips are present generation. In SoC chip also we have a monolithic, as I said before. Monolithic means the graphic card will be not integrated on a single chip. Okay, whereas a multi-chiplet means graphic card will be integrated on a single chip. Okay, and there will be multiple versions in that. Okay, so that is what the difference between ASIC, FPGA, and SoC. Everyone got the point?
Yes, ma'am.
Okay. Now, to design the ASIC chip, we need to follow several steps because those all are manufactured by the industries, by the product based companies. Okay, you already know a lot of product based company, Intel processors, you already know. Intel processors are designed by Intel company. They will buy some IPs from different companies and they will integrate IP and VIP from different companies. And there will be AMD processors will be there, and Samsung related processor, Qualcomm Snapdragon related processor, and these all are different types of chips. Every company have their own products. Okay, so all these chips will be manufactured with several steps. With lakhs of engineers involvement will be there to design a single chip. Okay, so for that purpose, we divide the whole process into several steps. Okay, front end is a one process, back end is the another process. Okay, In front end, we just do the designing and verification, like blueprint. We will get the blueprint of the processor, I mean chip. What is what? I mean what component should be placed in the chip. Just we'll get the blueprint. Backend is the entire manufacturing process. Okay, in a hardware, we will take whatever the blueprint circuit is generated. We will put that circuit into the chip. Okay, and floor plan, routing, everything concepts comes in the backend manufacturing process. Okay, in the middle, DFT insertion, logic synthesis, these all just gate level simulation, how we can check the testing. There are various kinds of testing, validation and verification. These all are testing part. Okay, so one by one we will discuss so that you will understand. Any doubts still here? Hello.
No, ma'am.
Okay. So front-end design verification flow. Mostly we have two domains, front-end domain and the back-end domain. Front-end is the design verification we call. Okay. So first of all, if you want to manufacture any chip, first we need to consider the specification. System specification. Okay. So what is mean by system specification? Suppose you are using some laptop, any company laptop, HP or Dell or Apple, whatever. uh, while you are buying, while you are purchasing something, you will check the specification, right? Like how many number of cores are there, or what is the battery size, or like how many drives you can there. Drives is not related to this. Mostly which type of processor it is, generation, we will check the generation, gen 3 or gen 5, gen 7. And like the RAM, what is the RAM, ROM, the size. Okay, what is the memory. So everything we will check. The battery related things, the processor core related things we will check. Like that in mobile phone also, what is the camera quality, what type of camera inserted, and what is the pixel quality, and the battery life, and number of cores we will check, and versions. There are a lot of things, right? So in the specification internally, but these are just a top view, but internally in the hardware point of view, how they will check means in terms of circuit design. Okay, for every feature there will be a circuit, something hardware circuit will be there. So they need to update every feature through hardware design, right? So if camera module is there, how the camera module will be inserted. Suppose iPhone, if you take if it is a max, there will be some three cameras will be there. If it is normal, two cameras. So that is total hardware part internally. Okay, so those type of things will come into the specification, all the features list. So if something is going to be popular in the market as per the user requirement, they need to get that specification for the next version. If something is not clicked in the market, they can remove that feature, right? So that is not useful in the market as per the user requirement. So all the things will come in the specification. There will be lot of teams will be there. Okay, nearly thousands of teams, lakhs of teams will be there internally. Okay, so every team will get some block. In SOC, I have shown you, right? In SOC, there will be thousands of teams will be there. I mean, thousands of blocks will be there like this. So it's a system on chip architecture, if you see. So it's a system on chip. What it consists of system on chip, like ROM or SRAM, DDR memory. It's a memory related, and some memory controller related, and there will be some processors, the bridge, and the peripherals, IO peripherals will be there. The protocols will be there, and these all are peripherals related. The power management related, RTC, RTIOS, the bus connections, and control signals. Okay, there will be lot of things involved in the single SoC. Like that, every IP will be divided into lot of blocks. There will be lot of teams in connected with the different types of IPs. Okay, so after getting a whole specification of any design, first we need to go with the architectural design. Okay, architectural design, in the sense, from specification we need to understand the logical design. Logical design, just a second. Okay, so first is the specification. After taking the specification, each blocks will be divided for different teams. So every team have some architectural design. Okay, some block will be designed into a architecture. Suppose I'm considering a multiplexer. Okay, 16 by 1 multiplexer using 4 by 1 mux. How we can draw a 16 by 1 mux using 4 by 1? First we need to understand the functionality of multiplexer, and then you can draw the architecture. For 16 by 1 mux using 4 by 1, there will be 4 multiplexers starting, and each multiplexer inputs are 4, here 4, and here 4, here 4, like that outputs will be connected here. So this is what overall architecture we will get. Okay, so this architecture we need to write the RTL coding. Why we are writing RTL coding? Because this architecture would be converted into the design, RTL design, through the coding. Okay, so to describe these digital circuits, we are using the hardware description language called Verilog HDL or VHDL. Okay, so this architecture will be converted into the code. Okay, after this code, the circuit will be look like this. Final circuit diagram. Yesterday I have shown you, right, after doing the synthesis, how the block is synthesized and how the circuit diagram is generated. So same process. Okay, that's what we call as a synthesis. Okay, after doing the synthesis, same circuit diagram we need to dump into the chip. Whatever the silicon wafers, the one of the semiconductor material we prefer is silicon compared to germanium, right? So into the silicon wafers, we need to dump this same architecture circuit. But can we dump directly without doing verification? We cannot dump. Why? Because verification is the major thing, because we don't know whether this circuit is correct or not. Maybe there will be some functional errors, or some connection issues may be there, or some interconnection issues may be there. Okay, there will be lot of debugging will be there. So that's why we need to do the functional verification. Okay, for doing functional verification, initially we can use a Verilog HDL, or else we have a languages called System Verilog and UVM, both for verification. Okay, so by using System Verilog language and universal verification methodology, UVM, we do the verification. We will check if everything is working perfectly, then we will send the design to the backend process. Okay, so here it is a backend process, physical design. Okay, everyone clear with front end? While doing the verification, if the requirements meet the functionality, we go to the backend process. If the requirement doesn't meet the functionality, we need to change in the RTL code. That means if any error is getting, or if any functional mismatches are there, to check again, we need to send the design to the RTL design engineers. Here we will get two type of engineers: RTL design engineer, verification engineer, or combinedly. Okay. Any doubts still here? Hello, are you there?
No.
No, ma'am. No doubts.
Okay. What about Sagar, Shranita,
Yes, ma'am.
Madhav? Okay, no doubts, huh? Okay, fine. So coming to the backend process. In the backend, before going to the physical design, there is a logic synthesis. In front end, we do logic synthesis. Synthesis is nothing but generating the circuit netlist and gate level netlist. The circuit will be generated into the gate level netlist and will be check the logic equivalence. That means whether the circuit, whether the gates are connected properly or not at a socket false, setup time, hold time, everything will be checked in the logic design and the DFT. Okay, so from node to node, point to point, we will check in the logic equivalence check. Okay, and then if everything is working properly, then the design will go to the floor planning. Floor planning is the first step in physical design. Okay, in physical design, first we will take a silicon wafer. Into the silicon wafer we need to dump the program, but we cannot dump directly. First we need to take the floor plan, same as like a house construction. I already told, right? In a house construction, how we do, first we will take the floor planning. So where we need to put the circuit, like in a architecture, which circuit should get, which component should get in a particular place. Suppose processor always be at the top. Okay, top left. And after main processor, central processing unit, there will be a graphic processor. After that, mostly memories will be there, and north bridge IO, south bridge IOs will be there, and here there will be a port connections or some IO peripherals will be there. The bus connection will be there in this middle. So every architecture we need to put into some plan. Okay. So after and also we need to check what is the size of each block. Like house, in house construction, however we check every room size, how much the hall should be, the kitchen should be, the like a room should be, the size particularly we will follow, right? So same here also we need to mention the particular size. So that's what floor plan, placement and clock tree analysis. That means where which component should place in which place. So that is what placement. Clock tree analysis in the sense making the clock connections for synchronization between all the circuits. Okay. Next routing, just wire connections and static timing analysis to check the setup time and hold time, because every clock edge, these two are majorly required to avoid the meta stability state and all. So there we will check the static timing analysis and physical verification and sign off. Every step we need to do the verification. Even after floor plan, there will be a verification step. After clock tree analysis, routing, static timing analysis, every step we need to do the verification. Why? Because without doing verification, we cannot go for next step. Maybe at any time we may have the errors. We need to do the debugging. Then only we need to follow next step. Okay. So finally, if everything is clear, after doing validation, after doing a pre-silicon testing and post-silicon verification, then tape off. Okay, tape off in the sense finally we can get the main processor, actual processor after doing the manufacturing. So that is what tape off. Okay, so these are the front end domain and the back end domain steps. Next, DFT, design for testability. DFT will get after synthesis, okay, before physical design and after front end domain. Middle there is a synthesis part, right? So there DFT DFT in the sense design for testability. So first we whatever the circuit generated netlist is there, we will check every like with respect to the scan chains will be there. Here we use the scan chains. That means suppose here there is a gate and here there is a gate. So here we will check every point to point with the socket faults and with the mechanism, BIST and ATPG mechanisms. We will check every point to point, node to node. Okay, in front end domain we use the DFT. In a back end domain also we have DFD, design for debugging. In the post silicon verification, that is also one role, designed for debugging. In the post silicon verification, we do the verification, debugging, everything in the post. That means after doing manufacturing. Okay, this is before doing manufacture. DFT team is after manufacturing. Okay, so this is what actual flow in the VLSI to design a ASIC chip. Everyone understood? So here you can check the DFT steps, a netlist. For the netlist, whatever netlist we can call, or RTL design or synthesized design. Okay, circuit diagram. We insert the scan chains and ATPG. Pattern simulations. After doing pattern simulation, if everything is correct, then floor plan, physical design process. Okay, clear till here? Any doubts? Hello.
Like,
Ma'am,
ma'am,
can you explain scan insertion?
Yeah, please tell. Yeah,
Could you explain scan insertion, ma'am?
scan insertion, huh? Okay.
Yeah.
Scan insertion in the sense, like there will be some JTAG. JTAG is related to the protocol connection. Scan insertions means it is a particular hardware to check in depth of the circuit. Okay, so chains. I don't know particularly in a DFT. I didn't worked in a DFT, but I worked in a DFD, design for debugging. Okay, design for debugging also same as a DFT only. In design for debugging, what we do in the sense, suppose there is a SOC, it is also related to scan chain only, but post silicon verification. It is a SOC, system on chip design. In the system on chip design, it's a hardware part. Okay, so in this SOC, we don't know whether it is working properly or not. There will be a debugging issues, there will be some errors are getting even in the post silicon. Okay, so we need to verify this hardware SOC. So it contains a processor here and the memory here and some IO ports here and some any IO peripherals. Okay, so to verify this, we insert the debug units. There will be some debug units, DBGSC modules will be there. So the debug units will be inserted like this. One debug unit like this. So this debug unit will be connected to here, and this debug unit is connected to here. This debug unit is connected to here. We call it as a cross trigger networking. Cross trigger networking is also same as a scan insertion. Scan insertion means by using the scanning techniques, it automatically check the where the error is getting. It just check it, scan the netlist, so where the error mistakes are there, so like that it will check. But in DFT we use the cross trigger network. So this is how it connect here, like cross trigger network. So by using this debug unit, every information will be taken into those blocks, particular blocks. So how we are going to debug some hardware by using the software, in the sense, this hardware we will connect to the Wombat. Wombat means it's a one type of circuit, FPGA circuit. It's a one type of FPGA circuit. Okay, through this FPGA circuit, we will connect a computer. In the computer, we will have a tool. In AMD, we have worked with the BCS tool, and here we will get the actual information of that circuit. Okay, so through those are the softwares. Okay, Vardi tools will be there, and there will be some other tools to check the scan chains and cross trigger networks for DFT. So through this Vardi tool, AMD use a Vardi, different companies use their own tools. Okay, so this is how we connect the cross trigger network and check the error issues into the software. Okay, by using the Wombat, and here this protocol connection is a JTAG. Mostly in a DFT, we use a JTAG protocol. Only in a DFT and a DFD. Remaining all teams uses a normal bus protocol like APB, AHB, AXI protocols, and these in PD we don't have mostly protocol. So here JTAG is mostly used, and remaining there will be a lot of protocols in every product based companies. Okay, but this is what actual scenario happened in DFD or DFT. Did you understood? However, here we
Yes,
insert however we put here the debug units to check the information of all the circuits. To these debug units, we will get the every information of these components, so that we can find easily where the error is getting. So directly we can debug that error. Debugging in the sense fixing that error. Okay, so we can fix the error directly by using the cross trigger network. Same scan chain also same like that only.
Ma'am, could you please correct me? These debug units will be built in the SOC, right?
Yes, it's a separate hardware we put in the SOC.
Okay.
Yeah.
Thank you, ma'am.
Okay. Any other doubts remaining? Okay. One day at the final stage, I will explain you the debug unit and how cross trigger networks are working, and the design for debug team in SOC, how they are working. I will take one session, SOC verification session. So you will get understand. Okay. Is it clear till here? And these all are theory content. I will share you the material, everyone. So you can go through the material and you can check. See here something given the description. So design for testability ensures that ASIC designs are testable for fabrication to detect the manufacturing defects. That means after synthesis. So netlist, you already know what is meant by netlist. Which having the components and gates, interconnections, everything. That circuit diagram we call as a netlist. Scan chain insertion in the sense, insertion involves adding scan chains. I told scan chains, right? Same as a cross trigger networks to the design. Scan chains are used to shift test patterns into and out of the circuit, inside the circuit and outside the circuit. It check the test patterns, and this modifies the netlist to include logic for testability such as scan flip-flops. So scan flip-flops also one of the circuit. By using those, we will take every logic data of all those gates. Okay, so in that one of the model is a BIST and ATPG. So ATPG means automatic test pattern generation. So automatically that there will be some test patterns like same. However, I kept drawn the cross trigger networks like this. There will be some test patterns like this. Okay, so to connect with the circuit. So by using these patterns, they will detect the faults, same as debugging unit. Okay, they will detect as the faults. So the test patterns are designed to maximize fault coverage, and during that as many potential defects as possible can be detected. So whatever the defects are there, everything will be defected by using those test patterns. And ATPG tools. For DFT also we will have separate tools. For PD we have the separate tools. For DFD we have separate tools like that. So ATPG tools analyze the modified netlist with scan chains to create effective test vectors. And next is a pattern simulation. So this is one of the verification methodology. Okay. So That is what front end domain, back end domain. So whole ASIC design flow from specification, architectural design, RTL design, logic synthesis, DFT, floor plan, placement, clock tree synthesis, routing, sign off, fabrication, packaging and testing, chip design finally. Any doubts still here? Hello.
Ma'am, what is meant by CTS?
Clock tree synthesis. That means the clock connections, the power management system will come here. Clock triggering networks, majorly clock connections between all the circuits, all the blocks.
Okay, ma'am. Okay.
It's not like a simple clock connection, but inside it there will be lot of connections. I think Sumalata can explain clearly because she worked in a physical design. Can you explain, Sumalata?
Yes, Prashanti. Yeah, clock of internal design is there, right? Some logic circuits, I mean standard cells and modules, black boxes, everything. We need to connect to the from a clock source. So from that, how the clock is building to meet the power and timing, like
Okay.
that. So basically, most there are so many clock structures are there, but mostly H3 clock structure is useful to meet power and timing.
Okay. Okay.
So when we open the tool, it will be visible. That is easily understand.
Okay. So actually here by using the low power analysis techniques or UPF techniques, we're also involved in the clock tree synthesis. So there are a lot of techniques actually in industries only we'll get to know about these things, how the low power analysis techniques and the clock tree analysis techniques. Okay. So simply it's a clock connection.
Ma'am, what exactly clock connection mean?
Clock connection in the sense the synchronization between all the circuits from SOC to the memory and the memory to some debugging unit and to IO peripherals. However, the synchronization, the clock connections.
For
Ma'am,
the flip-flop to enable clock is required, right? If the clock is enabled, so to reach each and flip-flop and each and logic gates, clock must be
Flip-flops,
there.
there will be billions of flip-flops in a one SOC. I'm just telling in a top level, but internally in a one SOC there will be billions of flip-flops. So in each flip-flop, how the clock is going to connect. That is what the synchronization. In this same point of time we will check the static timing analysis, how the setup time and hold time is working. If any clocking issues or getting the metastability state, whether it is able to like control the clocking gates and all. So everything will be checked in the clock tree synthesis.
okay, ma'am.
The power gating concepts will be there same here in the CTS only.
Okay, ma'am.
And next, so any other doubts here? Okay. Next, coming to the different types of hardware description language. So you already know what are the different type of HDLs are there. So mostly hardware description language is used to describe a digital circuit or an analog circuit. But here we are learning about the digital logic design. So mostly we will design the digital circuits. Okay. We have lot of languages like C, C++, Java, or to design a processor, we use the assembly language programming, the instructions and all. So every purpose we have different languages to develop some application or to develop some websites like that. But particularly to design a hardware digital circuits, we have VHDL and Verilog HDL. So VHDL have some limitations like it's a formal and it's a large use cases whatever we are writing. It is a more complex, that means we need to include the standard library. Whatever the functionality you are writing, we need to include the standard library for that. Suppose even if you are writing a mathematical calculations in the design, we need to include the math libraries. Like that, if you are using any gate level primitives, we need to include the standard library. So complexity is a more, and it's a strong simulation for verification, but only due to the complexity. For larger designs we cannot write the complex designs right in SOC level, and also it is difficult to learn compared to Verilog HDL. Using the Verilog HDL, it's a very flexible and also strong for simulation, easy to learn, and it supports the modular design and is simpler in mixing the procedural and data flow. We have a 4 different styles of programming, okay, like behavioral modeling, data flow modeling, gate level, switch level, like that, procedural assignment statements, continuous assignment statements. So to mix these type of signals, it is easy in a Verilog HDL. In terms of syntax also, it is a very closer to the C language, okay, so which is a simple to understand and to execute. That's why most of the beginners or experienced engineers, even in India, most of the industries and abroad countries also, Verilog is mostly preferred compared to VHDL. Okay, so that is what the major difference between Verilog and VHDL. And there is a system C and system Verilog. System C and system Verilog related to the verification part, purely verification part. System C is not mostly used, that is a older version. From system C only system Verilog introduced. Okay, so in our course curriculum, we are learning system Verilog, UVM methodology, and also scripting language after completion of Verilog. Okay. Any doubts still here?
Ma'am, like previously one ma'am, she worked in PD. Now she's taking course in verification.
Okay.
Is it that like
Who?
like
About who?
Sumalata ma'am?
Sumalata, no, she joined for PD. Just she joined for scripting, and she want to learn RTL design also.
Okay,
Yeah, only for RTL design, not for verification.
okay.
Okay. Any other doubts still here? So if you see the limitations of VHDL, like the steeper learning curve, which is a more complex and longer development time, and toolset limitations, which is not flexible. We cannot design in all tools. But for Verilog HDL, we have lot of tools. VHDL also we can use in the same tool, but it have some limitations. Okay, and mostly development comes for Verilog HDL only, because it's a popular language, right? Coming to the VHDL, so development side also VHDL have some drawbacks. Okay, that's why Verilog is mostly preferred. Coming to the advantages of Verilog, it's a simplicity and widely used, faster simulation, easy to learn. So getting started with the Verilog HDL. Today we will see the overview, the syntax and all. From tomorrow onwards, we will look into the coding part of all the uh, circuits. Okay, first we need to design all combinational logic circuits and then sequential, from full adder, half adder, multiplexer, hierarchical multiplexer, decoders, encoders, priority encoders, some binary to LCD segment display, and in flip-flops, latches, how to design a program in flip-flop latches. Not only learning basic things, we need to learn in an industrial way how you can crack a coding, like how simply you can write a program. Multiplexer can be designed in a 10 different styles also, but in 10 different styles, which one you will prefer a easy one? You can write the multiplexer in 10 number of lines, 20 number of lines also, but even single line also we can write the multiplexer program. Okay, so we need to learn those type of techniques, how we can write in a single line program for full adder, multiplexers, encoders, decoders. So those type of coding styles will be helpful in the project level. Why? Because in a project there will be lot of blocks, right? Suppose you are designing a simple router project. Okay, so in the router project it consists of some a synchronizer will be there, the final state mission will be there, and there will be some flip flops. Okay, and there will be some FIFO, FIFO1, FIFO2, FIFO3 memories will be there, and some other circuits there will be some arithmetic logical unit, a multiplexer. So there will be lot of blocks will be there in a one single circuit. Okay, so if you want to design all these blocks, you need to learn the techniques to write the program. If you write each block, like even small multiplexer also, if you write in a 20 lines of program, it takes a lot of time to design all the circuits. Okay, so we need to learn the easy techniques, how we can write a very simple programs for counters, registers. So if you learn in this way, while you are developing a complex projects, every simple code, every simple block you can design with a simple steps. Okay, no need to write a complex 10 number of lines, 20 number of lines for a single program, single design. Okay, so slowly we will learn those also. Next, coming to the levels of abstraction. So how many ways we can write a Verilog program normally? Okay, so first one is a behavioral modeling, next data flow modeling, gate level, switch level. I already told you, right? To design a digital logic circuit. Okay, so suppose a problem statement is given. To design a circuit to draw in a gate level netlist. So what are the steps we will follow? What are the steps we will follow? Suppose there is a priority encoder. I want to write a priority encoder program in Verilog HDL. First of all, I want to design a priority encoder in a gate level netlist. So how I can draw the circuit diagram? What are the steps I need to follow? Tell me. What are the steps we need to follow to draw a circuit diagram? Any circuit diagram.
First,
Truth
we need
table,
to.
yeah, truth table and logic simplification using K-map techniques.
Okay.
Then we will get the algebraic expression, Boolean expression. Then we will select the gates. We will implement.
Okay. Pranita, your answer?
We need to know the truth table first.
How do you know the truth table? How can you know the functionality? From the problem statement, you will get to know the functionality, right? How it is working and what are the inputs, what are the outputs.
Yes.
Okay. Then So first of all, whatever the problem statement is given, okay, you need to understand the functionality. Okay, I want to design a LED display. Okay, so LED display or LCD display. Suppose LCD display, how many number of values it will count from 0 to 9. So LCD display will look like this. Okay, I am giving the problem statement that I should I should design a LCD display. Okay, so here what are the inputs and what are the outputs you need to understand. So how many number of combinations we will get and how many number of inputs will be there for LCD display? How many number of inputs and how many possible combinations will be there to display? Madhav?
Sorry, ma'am, no idea.
How many number of values it will display?
0 to 9 BCD.
0 to 9. Okay,
Yeah.
0 to 9 means how many number of input combinations?
4.
There will be 4 number of inputs. Okay, 4 number of inputs means how many combinations?
16.
16 combinations. Okay, so now you got the functionality of LCD display. Okay, after getting the functionality, first one is you need to draw. The first step is to draw the block diagram. So how many number of inputs will be there? So 4 number of inputs. How many number of outputs will be there? Whether it have a control signal or not. In flip-flops, latches, registers, counters, we have a control signals. Nothing but clock, reset. We call it as a control signals, right? So remaining combinational logic circuit, we have a enable signals. Enable signal is a control signal. So you need to write the control signal. Please mute yourself. Please mute. So we need to draw the block diagram first. Okay. After drawing the block diagram, now you will understand how many inputs, how many outputs. So based on that, you need to draw the truth table. So 4 number of inputs and 1 output will be there. Whatever, according to the circuit diagram, you will draw the truth table. So whatever the output is there, you need to write the output expression in the second step. Okay, so here output expression. From the output expression, third step is a circuit diagram. So how you will draw the circuit diagram in a gate level netlist? So by using the basic gates, universal logic gates, you will be drawing the gate level netlist. Fourth step is from the gates, you can convert the circuit basic gates into the CMOS. Okay, so gate level netlist into the CMOS transistors you are generating. So this is how we draw the digital circuit and finally we get the gate level circuit. Okay, so same LCD also, how you will draw design a Verilog program for LCD. First we will draw the truth table. What is the truth table? A, B, C, D or the inputs. So there will be a combination 0, 0, 0, 0, 0, 0, 1. 16 combinations are there. In those 16 combinations, first 0. 0 means which light will be on and which light will be off. So outputs. Okay. All are erased. In this control Z is not working off. Okay. See, LCD display. So 4 number of inputs will be there and how many number of outputs will be there? A, suppose X, Y, Z, W are the inputs. A, B, C, D, E, F, G. These are the outputs. Okay. So if input is 0, 0, 0, 0, then what are the outputs? That means which light will be glow. That means 0 means which light will be glow. This one will glow. This, this, this. That means all are ones except G. Except G, remaining all are 1. Next one is a 0, 1. Suppose 0, 0, 0, 1. 0, 0, 0, 1. 1 means only B, C will be on. Remaining all outputs are 0. Next, 8. 8 means 1, 0, 0. 8 means all will on like this. All lights will on. Next, 9. 9 means 1, 0, 0, 1. 9 means only these will be on except E, D will be 0, 0. That means for this particular LED, the truth table is 4 inputs and 9 number of outputs. 9 A, B, C, D, E, F, G. So those many outputs. From those output, whatever the circuit, whatever ones we have based on the POS and SOP format, we write the output expression. From the output expression, we draw the gate level circuit netlist. From the gate level circuit netlist, we draw the CMOS level circuit diagram. So these are the steps we need to follow. Same in Verilog HDL also, we can write the program in these many models. Okay. First model is a behavioral modeling. First is a behavioral modeling. That means at this level, we only focus into how the functionality is working. That means if you write the programming by using the truth table, that's what we call as a behavioral modeling. If you write the program using the truth table. Next, if you write the program using the data flow level, that's what we call as a output expression. If you write the program using the output expression, then it's called data flow model. If you write the program using the gate level circuit netlist, then we call as a gate level circuit. And if you write the program by using the CMOS level, we can call it as a switch level circuit. Did you got the point now?
Ma'am, can you repeat once again?
If you write the program by using the truth table, we can call it as a behavioral modeling. If you write the program by using the expression, output expression, suppose full adder is there. Full adder, we get the two expressions, sum, carry. Sum equal to A into B, carry equal to sum equal to A XOR B, carry equal to A into B into AB plus BC plus CA. Sum equal to A XOR B XOR C. So that's what we write here, expressions directly. Gate level netlist, in the sense for full adder we have the gates. So one XOR gate here. Yesterday I have shown you, right, while doing the synthesis. So that program is a gate level. That means by using the gate primitives we write the program. Next is a switch level. Switch level means by using the CMOS transistors we write the program. So these are the 4 levels of modeling. Did you got the point? Hello.
Yes, ma'am.
Any doubts still here? Like that, any circuit diagram, even it's a full adder or multiplexer or LCD display or BCD or even finite state machine memories, every design you can write in these many models. One is a behavioral model. There we use the truth table. By using the truth table, we write the program. Data flow, by using the output same here. However, we draw the truth table first and then expression from the truth table, gate circuit from the expression, and CMOS level circuit from the gates. Same in Verilog also, we will follow 4 different styles. Okay. If you don't have any doubts here, we can go with the next session. Next topic. Hello.
Please go ahead, Prashant.
Are you all sleeping? Sagar, Pranita, Lahari, Madhumita?
No, ma'am.
Then what you are doing? Can't you answer? I don't expect this type of response from next time. If you are not interested to join, I can quit. It's not at all a problem for me. Go through the concepts till here. We will discuss in the next session. In the next session, we will discuss on how to write the program for behavioral modeling, data flow, gate level, switch level, and also we'll see the syntax, how to write the program. Okay, the syntax and how we can use the synthesis and simulation tools. Okay, Pranita, can you share your screen where you are stucking?
Yeah, ma'am, I just reinstalled it. The problem was solved actually. I'm now installing all the setups.
Okay, now it's
Yeah.
working.
Yeah, yes, ma'am.
Okay, okay, fine. What about Aryan? Hi, Aryan. Okay. Yeah, Madhav, do you have any doubts?
Yeah, ma'am. Actually, I need that link to install the software.
Yeah, I will share you the recorded session. It's a huge process. Even I tell now, maybe you may not understand. Okay. Yesterday I have recorded till installation process and how to use the tool. I will share the link and you can install. If you have facing any problem, I can we can connect in the session. Okay.
Okay, ma'am. I will go through once and I will try to install. If anything, I will ask you.
Yeah, sure.
Thank you.
Ma'am, why we need two tools like Cortex Prime and this one?
Why? Because Quartus Prime is for synthesis. We cannot do the simulation by using Quartus Prime. For simulation, we need to use the simulator, model simulator. Why? Because if you see here, the flow, first RTL coding and then verification is there. So here to design a RTL, we are using the Quartus Prime. To do the verification, that means simulation, we are using the model simulator. That is only for Verilog HDL. Once we move to the system Verilog and UVM, we need to use some more tools because these are basic versions. But system Verilog and UVM, we cannot do the verification in simulator, model simulator. So there we use a different tool. Okay. For simulation, you can also use an online tool called EDA Playground. So uh, in a Google, you can open edaplayground.com. Here you can do only simulation. Okay. In the coming sessions, I will tell you how to do the simulation. So you can also use the EDA Playground. Mostly I will use EDA Playground only. Why? Because it doesn't take lot of time. Normal tools, we need to follow several steps to do the synthesis or to do simulation. We need to we need to run multiple files. Okay. So EDA Playground is the best in my case. Okay, you need to prefer the tools only. For explanation, it is good for me, so that's why I use the EDA only. But while you are practicing, better you use the tools only for System Verilog and UVM also. Okay, if you don't have a tool, you can use the EDA here. Left side there are tools and simulators, right? You can select a tool here, Aldeck tool. If you have a college mail ID or your office mail ID, you can also take the access from Cadence, Siemens and Synopsys tools. Okay, only for official mail IDs, they will provide the access for Cadence, Siemens, and Synopsys. Remaining all deck is best. Okay, so left side you can write the test bench, here test bench code, and right side is the design code. Okay, so we can do the simulation and we will check the output here like that. We will see in the next session those things. Any
Ma'am,
doubts?
this
Yeah.
system Verilog UVM is there now, ma'am. This both are useful for DV and formal verification, right?
Formal verification means it's a assertion based verification. We need to learn deep into the assertions majorly. So in system verilog we will discuss coverage and assertions. So formal verification also will come into the same.
Oh.
Yeah. But for fresher, are you fresher or experienced? Hmm?
Fresher only, ma'am.
Fresher only, right? You
Yeah.
are studying MTech. So
Yeah.
for freshers, we don't have any formal verification roles. Very rare. For experienced engineers only, we will have the formal verification.
Okay.
Okay. You need to go with the verification, functional verification only, not formal verification.
Okay.
After getting into the industry, there you need to decide what project you get. Suppose if you get in a SOC based project, next whenever you are trying to change the shift, when you go to the next company, there you can mention whether you are SOC based verification or IP level verification or formal verification, or there it totally depends on what type of project you are doing here. Based on that, you can change your designation. Okay.
Okay, ma'am.
Okay. So Wednesday, next session is on it, because from next session onwards you will be getting Verilog assignments. Okay. So parallelly you need to work.